Good morning. We are continuing with Ampere's law today. Ampere's law, sort of our Gauss's law equivalent for magnetic fields. And it only works really in two cases. An infinitely long straight wire. It does not work for wire segments that are not infinitely long. Only an infinitely long wire segment, straight, or solenoids. So we did sort of an example with the infinitely long wire. We did the magnetic field outside of the wire and even the magnetic field inside of the wire if the wire has some cross-sectional area associated with it. So today we will do a solenoid. We'll start off with the solenoid because it's turns out to be a very simple way of finding the magnetic field inside a solenoid. Solenoid, it's just a coil of wire, fancy name for a coil of wire, right? And I don't know why we have so many names for a coil of wire, but we're going to call it an inductor in a couple of weeks. So now it's a solenoid, it's going to be an inductor pretty soon, but we have a lot of different names for a coil of wire. All right, so if we were to draw this, it would look something like this. And, you know, even with my artistic ability, it's hard to see exactly what's going on there, right? So the way we typically draw this, so it's a little easier to kind of see what's happening, is it's like we're taking a saw and cutting it down the middle and opening it up and looking at a cross-sectional area of the solenoid. So if we do that, it kind of looks like this. On this side over here, we see a coil of wire. And on the other side over here, we see a coil of wire. Right, and I can just keep going down the list here, and all I'm drawing is that cross section. If I cut the solenoid right down the middle, that's what I would see right there. Right, maybe I'll do something like that. How's that? And I pick a current. Let's say the current is going this way. So on this side, it's going into the page. And on this side, it would be coming out of the page. And then it's going into the page, coming out of the page, in and out, all the way up the solenoid. I actually wanted to let me start out with the coils not quite packed so closely together, and let's move in that direction and see what happens to the magnetic field. Each one of these wires, current carrying wires, fills the space around it with a magnetic field. It forms circular paths around the wire. The magnetic field forms circular paths around the wire. Let's see what color. How about blue for magnetic field? So this wire is going to have a magnetic field that goes around it like this. What direction? Counterclockwise, right? Magnetic field will look something like that. And this wire also will have a magnetic field that looks something like that. And the ones on the other side will do the same thing. Those will be going clockwise. And then if we step back a little bit, there'll be another magnetic field line we can draw. It's going to look something like this. And there's going to be one that goes right down the middle. And then there'll be another one. I'll kind of come back over here. Probably something like that. Over here, similarly. And then maybe one that kind of comes down here like this. Something like that. Okay, so there's my magnetic field, roughly. As we pinch those coils closer and closer together, the fields on the outside get stretched out more and more. It gets reduced. The effect on the outside gets reduced, and the effect on the inside becomes more and more uniform. Okay. So as it becomes this turns into this. Oops. Then on the outside, I guess I could add a few more here, but you get the idea. On the outside, B goes to 0. And on the inside, B is uniform. And this is what we call an ideal solenoid. So it's not that different than what we did with charge. Remember, we said if we have a point charge, the electric field goes out in all directions. But if we spread that charge out over some distance, it starts to, in the middle here, it starts to do something like that. Then at the ends, it kind of looks more like the point charge, right? But then as we spread that out more and more, if we make it infinitely long, then the electric field becomes uniform, right? or with a capacitor. Actually, with the capacitor maybe is a better example, not just a sheet, a capacitor. With the capacitor, you start with a small region like this, and some of the charges come over. Some of the charges get attracted over, but some stay on the outside, right? And you've got something like that, right? But as you make those longer and longer, then all the charges come over, right? E goes to 0 out here, right? And E is uniform in between the plates, right? So it's very similar, right? The analogy we're using here is it's very similar. As we make this solenoid into an ideal solenoid, then the magnetic field inside becomes constant, the magnetic field outside becomes 0. Okay, so how do we make it? First thing we need are those turns to be very tightly packed, very close together. Turns very close together. And the other thing we need is that it needs to become sort of infinitely long, or the length needs to be much, much greater than the radius is another way of approaching an infinite length, right? And if we get there, if we get to this ideal solenoid, we know the internal magnetic field is uniform, and the external field is 0. All right. Now that we know what a solenoid is and what an ideal solenoid is and how to approach an ideal solenoid, let's try to use Ampere's law to figure out what the magnetic field is inside of an ideal solenoid. Okay, let me draw my cross-sectional view of my solenoid. Have it coming out on this side, in on this side. That means my magnetic field is going to point which way? that way. Ampere's law tells us that the integral around a closed path, b dot ds, is mu naught times I enclosed by that path. Okay, let's pick a path. I will pick a path. I will show you a nice path to use. Let's use red. That's going to be my path. So I will number my sides. I will call this side over here 1. Where am I going to put my 1? 1, 2, 3. Actually, let me break this up. I'm going to call this one 2, and this one 3, 4, 5, and 6. I'm going to integrate around the whole path. So that means I'm integrating along side 1, side 2, side 3, side 4, side 5, and side 6. I have to break this integral up to get all of them, right? Integral over 1 b dot ds plus the integral over side 2 plus the integral over side 3. You get the idea. Plus dot dot. Well, I'll write them all out here. Okay, let's look at them one at a time. B dot ds for side 1. B and ds are parallel, right? So the dot product is just going to give us 1 or minus 1. Let's go around the loop in the direction of the magnetic field. So it'll give us 1. Okay. They point in the same direction, right? B, where side 1 is on the interior of our solenoid, right? So B, we know B points straight down. And side 1 is parallel to that. So ds is either going to point this way or it's going to point that way. We don't really care which way. The minus sign is not important. Let's just pick our path to go counterclockwise so our ds points in the same direction as B along side 1. And so the dot product goes away. So now we have the integral of B ds. B is constant inside that solenoid, so it comes out of the integral. So this integral is just B times the integral of ds, which is the length of side 1. Let's call that L. Let's call that length L. Let's do the next one, segment 2. What do we get for B dot ds along segment? Segment 2 is this one right here. Right, that's segment 2, that section that's going horizontal, but still inside of the solenoid. We get 0 for that section because B points towards the bottom of the page, ds points to the left, so the dot product gives us 0 there. How about sections 3, 4, and 5? They're all going to be 0 because B is equal to 0 outside of the solenoid. Why did these disappear on me? 4. Okay, so for sections 3, 4, and 5, and section 6 is the same as section 2. So the dot product gives us 0. What do we end up with? We end up with B times L on the left side. And on the right side, we have mu I enclosed. What is I enclosed? Well, if I look at this, I've got 1, 2, 3. I've got 3 turns. I happen to pick 3 turns that I enclosed when I drew my path for Ampere's law. Maybe you chose a different number on yours. I don't know. But you can see that there are multiple turns there. So let's just call it N. Capital N is the number of turns enclosed. That's the number of turns inside the path. I've got B times the length is mu naught capital N I. And I divide both sides by L. I get the magnetic field inside a solenoid is some constant times N I over L. That's what you got when you did your lab. Magnetic field inside that slinky. You said it was proportional to N, proportional to I, inversely proportional to L. And if you solve for that constant, you got something like 4 pi times 10 to the minus 7, hopefully. The way we typically write this is because our solenoid is very long, right? It could be infinitely long. It's very long. The way we typically would write this is mu naught lowercase n I, and lowercase n is the number of turns per length. Then the solenoid could be as long or as short as we want. All we care about is the turns per unit length, which kind of makes sense because it shouldn't depend on if I chose a bigger dimension or you chose a smaller one or whatever. We shouldn't get different answers, right? So it turns out we all get the same. My L might be bigger. If my L is bigger than yours, if I had a bigger length on the side of my Ampere loop, then I'm going to have a bigger number of turns enclosed, but the ratio is going to be the same for all of us. All right, so one thing if we were to use a curved path, now let me make it a little. If we had a curved path like this for our current, the magnetic field is going to form loops around this current carrying wire. It would be into the page on one side and out of the page on the other side. And this would be sort of we could draw a line that's perpendicular to our current carrying path, our current carrying wire. And then we could come up here and do the same thing. We'd have a magnetic field that's into the page over here and out over there, right? So it's something like that. And then we could come over here and do the same thing. You can see that the magnetic field on one side of that wire is stronger than the magnetic field on the other side of the wire. You bend that wire around and the field that's going into the page on the right side or below the wire is going to be stronger. Those are closer together. The X's are closer together than the dots are. So the magnetic field on one side is stronger than the magnetic field on the other side. Now, there's no nice path you could pick going around this wire that the integral of b dot ds is easy to solve, right? So because we don't have any nice path to use for our Ampere's law, we would use the Biot-Savart law. There's another complication here, and that is that with Gauss's law, remember Gauss's law was always true. It just sometimes was ugly, and you were better off just integrating over the charge distribution. Ampere's law is not always true. Ampere's law had to be modified. We're going to learn later on. We're learning sort of a special case of Ampere's law when the fields aren't changing in time. But when you only have finite segments, then I believe time plays a role. And so because Ampere's law, the way we're learning it, is not complete, that limits the way we can apply it also. So it only works, the way we're learning Ampere's law, two cases: straight infinite wires, not segments, not straight segments, no, straight infinite wires have to be infinite, or ideal solenoids. Right? Those are the only two times we use Ampere's law. Ideal. Okay, let's talk about magnetic flux for a minute. Flux, we know the definition of flux, integral of E dot dA over some surface, right? And magnetic flux, integral of B dot dA over some surface. And Gauss's law told us that the flux, electric flux, was Q in over epsilon naught. Excuse me. Let's just draw some electric field lines real quickly. And let's draw a magnet. Something like that, right? You get the idea. Okay, so now I should have made it symmetric here. Hold on. Boy, that's ugly. Okay, not as ugly. All right, so there's our magnet. If we pick some path here, I'll use red. Pick some path, then we can say that the flux, the net flux, is the proportional, right, to the charge enclosed. If we come over here, and we can tell there's excess charge enclosed because we have more field lines coming out of our Gaussian surface than we have going in, or vice versa, right? Either way. If I do the same thing for my magnetic field, what do I get? I always have the same number of lines entering my enclosed surface as I have exiting the closed surface, because they form closed loops. The magnetic field lines always form closed loops. That tells me that this is zero. That's Gauss's law. For magnetism. Integral around a closed area, surface is zero. Yeah, I should have drawn fewer lines. But for everyone going out, the important point here, for everyone going out, there's one going in the other side, right? There's a pair. They all pair up. Gauss's law for magnetism. This is by observation, okay? We've come to this conclusion by observation. What does it tell us? It tells us there are no magnetic monopoles. North and south poles always come together. The electric charges, we can have a positive charge or a negative charge. They don't always come as a pair. We can have a positive charge by itself, and so we can have a net flux. We can have more positive charges inside of a region than negatives, or vice versa. But magnetic poles do not come individually as norths and souths. They always come as a pair, a north and a south together. So you can't just enclose a north pole. They always come as a pair. There are no magnetic monopoles. That's what this equation tells us. And that's by observation. I don't think there are any laws of physics that prohibit magnetic monopoles. And we do have some theories that predict that they exist. I think they may have even been able to create them momentarily in a lab, but we haven't found any in nature. Ampere's law, as we learned it. Integral b dot ds is mu naught I enclosed. This helps us to find B from current. But Maxwell came along and said Ampere's law isn't quite right. We need to modify it to make it more universal. So we call that the Ampere Maxwell. Ampere Maxwell law. And it says that the integral of B dot ds around a closed loop is not only mu naught I, it is also has a contribution from a changing electric field. So what does this tell us? It tells us that the first part tells us the magnetic field created by a current. And the second part says the magnetic field could be created by a time-changing electric field, an electric field that's changing in time. Created by a changing electric field. All right, so something interesting just happened. A changing electric field can create a magnetic field. It turns out that a changing magnetic field can create an electric field. And a lot of debate and interest in the early part of late 1800s and early 1900s is about light and what is light exactly. Is it a particle? Is it a wave? Is it this? Is it that? We know now it's part of the electromagnetic spectrum. We have X-rays, ultraviolet, visible light, gamma rays. We have microwaves, infrared. We call it all electromagnetic waves. It's all the same stuff. We give it different names. We call one section of it a microwave, and another section a gamma wave, and another section infrared, and another section visible light. We call it different things just because of where it falls, how much energy, but really it's all the same stuff, right? It's just an electromagnetic wave. What is an electromagnetic wave? It's a wave, something in a wave is oscillating, right? And in this case, what's oscillating? The electric and magnetic fields. It's a wave made up of electric and magnetic fields, and they oscillate. The magnetic field goes up, the electric field goes down, and vice versa. As the electric field changes, the magnetic field changes, and they generate each other. The question is, how do they propagate? So a wave typically needs a medium to propagate through, right? Something is oscillating. Sound is a pressure wave. It's a vibration that gets transmitted through the air or through a solid or through a liquid. It needs a medium to propagate through. Waves in the water, right, need the water to propagate through, things like that. So an electromagnetic wave, it turns out, does not need a medium. It can propagate through the vacuum of space, luckily for us, because light can get to us from the sun. But there's something special about this, the way that the wave propagates itself. When the changing electric field creates the magnetic field and vice versa, and it propagates like that. And Maxwell came along and said, you know, if he looked at this carefully enough and did the math, the wave had to propagate at a certain speed. If it went slower than that, then the energy would get lost somehow. The energy in one field wouldn't quite get transferred to the other field, and the wave would somehow disappear, and the energy would poof, magically go away. I don't know. Didn't make sense, right? If the wave was going too fast, it would take more energy to get from the electric field to go into the magnetic field, and vice versa. You wouldn't have enough energy. You'd have to constantly be adding more energy, and that doesn't happen, right? But there's a special speed that the wave propagates at where the energy transfer is just right. The energy from the electric field ends up in the magnetic field, and the energy from the magnetic field goes back into the electric field. And that speed is 1 over the square root of mu naught epsilon naught. The speed of light. Maxwell did a mathematical derivation and determined the speed of light mathematically from this relationship. So you might not have seen that coming. This epsilon naught constant that we've been using with our electrostatics equations, this mu naught constant with our magnetic equations, 1 over the square root of mu naught epsilon naught is the speed of light. Very interesting. Okay. Hopefully I blew your mind a little bit right there. Maybe that's a good place to stop. Oh, good. That is a good place to stop. So we will continue with magnetic fields and using we'll talk a little bit about permanent magnets and magnetizing and demagnetizing magnets. and then we'll get into Faraday's law. Faraday's law is really exciting because it sort of brings together a lot of the things that we've been learning and really good applications, right? We know we can generate electricity. Faraday's law tells us how we can do that. It tells us how motors work and some intricacies with that. So we'll get into that a little bit. Okay. So have a good weekend. We do have a review this afternoon, right? In an hour or something, 2 hours, 2 hours. So if you're interested, come to that. Otherwise, have a good weekend. We'll see you next time.
Professor Frank, I got a question if I may.
Go ahead.